Fusion energy has long been called the holy grail of clean power. Commonwealth Fusion Systems, or CFS, is leading the way with SPARC, a compact fusion reactor that could deliver city-scale electricity without carbon emissions. Their mission is to prove that fusion can move from science fiction to commercial reality in this decade. At its core, fusion is the same process that powers the sun. Deuterium and tritium nuclei fuse at around 150 million degrees Celsius, producing helium, a high-energy neutron, and vast amount of energy. To achieve this, tokamaks use powerful magnetic fields to contain the plasma. Success is measured by Q, the ratio of fusion output to input, and the ultimate goal is Q greater than 1. What sets CFS apart is its use of high-temperature superconductors called Rebecco tape. In 2021, they built the strongest fusion magnet, over at 20 Tesla, proving the technology at scale. These magnets make it possible to shrink reactor size dramatically while still producing the same power, a game-changing advantage. SPARC's designs show how powerful this approach is. It has major radius of only 1.85 meters, yet generates a 12.2 Tesla magnetic field and carries 8.7 million amps of plasma current. The critical mission is to achieve Q above 2, demonstrating net energy gain for the first time in a computer reactor. Here's how SPARC is built. Rebecco toroidal field coil wraps up around to confine the plasma. A central solenoid drives the plasma current like a transformer. The vacuum vessel houses the plasma under extreme conditions, while the diverter removes impurities and protects the wall. It's a remarkable feat of engineering. To make fusion work, SPARC uses multiple subsystems. Heating comes from neural beam injection and radio frequency subsystems. Fuel is delivered with precise deuterium-tritium pellets. Advanced diagnostics monitor plasma in real time, and safety systems mitigate disruptions. A key innovation is demount Rebecco coils, which can be assembled and serviced unlike traditional permanent magnets. The progress has been rapid. In 2021, 20 Tesla magnet was demonstrated. By 2024, plans for ARC, a 400 megawatt pilot plant, were unveiled. And in 2025, SPARC's assembly began at Devens, Massachusetts, along major partnerships, including a 200 megawatt deal with Google and $1 billion investment from ENI. SPARC role is to prove net energy gain in a compact tokamak. Once successful, the design scales into ARC, a 400 megawatt pilot plant featuring a liquid FLIB blanket for tritium breeding and power extraction. ARC is the bridge from proof of concept to full commercial fusion. Fusion's impact is huge. It can deliver firm, zero-carbon baseload power for energy-intensive industries. Data centers, which need 24/7 reliable power, can run without carbon emissions. And the high-temperature heat from the reactors make hydrogen production efficient, supporting clean fuel transitions. The roadmap is clear. First, complete SPARC assembly and testing. Next, achieve first plasma to demonstrate confinement, then move into deuterium-tritium operations targeting Q above 2, finally scale to ARC deployment in the early 2030s, delivering clean, abundant energy at grid scale. Fusion safety is also a strength. There is no chain in reaction risk, and the systems shut down inherently. In just a few years, CFS has gone from magnet breakthroughs to assembling a reactor with corporate buyers lined up. If milestones stay on track, SPARC and ARC could mark the decade when fusion power left the lab and entered the grid, transforming how we power cities, industries, and our future. Thank you.